the 8th Undergraduate Virtual Research Competition. In this presentation, we will analyze the energy and exergy efficiencies of the solar air heater using baffles. We will go through the introduction, application, motivation, problem statement, objectives, then the overview, methodology, results, project management, and then the conclusion. With the world's energy demand growing day by day, it has become a mandatory obligation to humankind to find alternatives to replace the limited supply of energy sources available as of today. Moreover, Dubai has launched its 2050 Clean Energy Strategy, where it aims to produce clean energy. Therefore, we aim to design solar air heater in which it is considered as one of the main environmentally power assessed, where it can be used in many different applications.
Solar air heater application, space heating, drying, and solar water distillation. Space heating, solar air heater are especially well known for space heating applications since of their straightforward design and cost. They can be done handcrafted of an available material. Space heating in a radiator system requires temperature of 50 to 70 Celsius. Modern low energy building equipped with a floor heating that requires temperature of 30 to 40 Celsius. Crop drying solar air heater is important as it protects grains, fruit, vegetable, or meat from rodents, mildew, and even to store them for later use. Solar water desalination is a technique to produce water with a low salt concentration from seawater by solar air heating. The temperature of saline water is usually raised up to 60 Celsius, which is relatively low water temperature, which is give the HDH process an advantage.
Talking about what motivated us the most to choose this topic, as mentioned by my colleague, we are motivated by the wide application of solar air heaters. Second, as we all know that solar energy is plentiful and a clean energy, which means that it is environmental friendly and there are no greenhouse gases emissions, while fossil fuels are the absolute opposites. They have been causing well-being issues and affecting the environment negatively.
Aside from solar air collector simple design and low assembling cost, solar air heater has different restrictions. For example, the low thermal conductivity of the air and low heat transfer coefficient. To overcome these limitations, we will attempt to increase its performance by utilizing the heat transfer coefficient by inserting baffles, suitable absorber plate material coating, and glazing.
Our objectives to calculate the efficiencies of solar air heater and ways to increase both exergy and energy efficiency, to compare between different glazing absorber material and system with baffles and without baffles, to build an experimental setup of a system with the best glazing absorber material and baffles, to simulate solar air heater using ANSYS.
Our solar air heater consists of the following components. On the very top, we have the glazing, which reduces the thermal losses and transmits solar radiation to the absorber plate. The airflow will be between the glazing and the tandem absorber plate, where baffles will be added on top of the absorber plate to increase the turbulence. Furthermore, the insulation will be on the bottom of the absorber plate as well as on the edge of the solar air heater to avoid losses. An orifice meter is added to measure the flow rate of the air. A manometer is also added to measure the air pressure. Also, a wind velocity and the solar radiation measurement will be added when doing the experimental work. In order to choose the best design for our solar air heater, we have been comparing materials of components used. For the tandem absorber plate design, we will be comparing carbon nanotubes and copper oxide and without copper oxide. The spectral selectivity depends on the emissivity and absorptivity of the material, and optimum selectivity is obtained from high absorptivity and the lowest possible emissivity. As shown in figure A, this is how the absorber plate will look like with black paint only. Whereas the figure B shows how it will look like with carbon nanotubes and copper oxide. Because of the plump microstructure of the new coating, multiple reflections are created, while that will decrease the emittance of the absorber plate.
Generally, there are always top losses from the solar collector. So to minimize the thermal loss, glazing is placed on the top of the absorber plate. In our design, we will compare between cellulite fiberglass and polyvinyl fluoride. Cellulite fiberglass is a new proposed design. It is a non-glass reinforced with all existing plastics, which is easy to handle, resist breakage, and cheap. However, polyvinyl fluoride is an exclusive polymer, special plastic. They have good properties such as mechanical strength and high chemical resistance.
Baffles usually are placed between glazing and absorber plate, exactly at the top of the absorber plate. There are many different types. We have chosen a rectangular shape baffle, which is the most used one because it has higher thermal performance than the other shapes and aluminum porous material in order to increase the rate of heat transfer. The best positioning when all the air channels are 100%, which poses the highest thermal efficiency. Comparing baffle in staggered and non-staggered and no baffles, as we can see in the figures. With baffles, there is a staggered and non-staggered array. In our design, the baffle configuration we have chosen is a staggered array flow that results in obtaining the higher heat transfer and more turbulence in order to increase the Reynolds number, and also it can guide the air easily. Without baffles, we will have no turbulence and it will not enhance the system.
For the calculation part, these are the main equations used. We have calculated absorber radiation for the three cases as well as the loss coefficients. For the useful energy, we have assumed the fluid temperature and made iterations in order to find the plate and cover temperature. Lastly, we have found the energy and exergy for the three cases with and without baffles.
These equations are found to calculate the area of the collector with baffles, and in the case of no baffles, the area of the collector will be equal to the total area.
For the first material, we used the polyvinyl fluoride for glazing and aluminum plate coated with 4% cupric oxide and carbon nanotubes for the absorber plate. Comparing the energy efficiency without baffles and with the baffles will result in 17.05% enhancement when baffles are attached due to the smaller area reduction. The exergy efficiency is dramatically lower than the energy efficiency, and this is considered to be the desirable case.
Second material, to compare the glazing material, we found that for non-baffled and baffled, the useful energy is the same, while the area of reduction decreases, but the energy efficiency and exergy efficiency have been increased compared to the first material.
For the third case, we have chosen the polyvinyl fluoride and aluminum plate coated with 4% carbon nanotubes only to see the effect of carbon oxide. As seen from the results, the energy efficiency for this case is lower than the energy efficiency with carbon oxide. As in the first case, the energy efficiency enhancement was found to be 26% after adding baffles, while the exergy efficiency didn't change much. As a result, we will be using cellulite fiberglass and aluminum plate coated with 4% carbon nanotubes and carbon oxide, as it gave us the highest efficiency. We have summarized the cost of the components and materials needed to design our system, and the total cost was 6,144 dirhams.
Here is the SDP1 Gantt chart that summarized our work during the semester.
In conclusion, we have achieved our goal. Different materials were compared for the absorber plate and glazing material with the insertion of baffles. Thank you.